Exercise 8.3 brings us to the famous game of chicken. And the game of chicken is played by two macho teens who speed toward each other on a single lane road. And the first to veer off, that is pulling the steering wheel to the left or right, is branded the chicken, whereas the one who doesn't veer gains peer group esteem. And you don't want to be branded the chicken, so you lose. And peer group esteem is something that everyone longs for in life, so then you win. Of course, if neither veers, they bump into each other, they both die in a crash that will be the result, and the payoff will be negative to both. And payoffs to the chicken game are provided in the following table. So we have two teams, Team 1 and Team 2, because it's illegal, so we don't give names here. And if both veer, well, they both live, so that's not too bad. But both are actually chickens, so they get a payoff of 2. If they both don't veer, both will die. It's not a good outcome for either. They both get a payoff of 0. And if player team 2 veers and player team 1 doesn't veer, it's great for team 1. He or she gains the peer esteem. And team 2 is branded the chicken and only receives a payoff of 1. But still is alive. And opposite, if team 1 veers and team 2 doesn't veer, then the bigger payoff goes to team 2. Well, this with the single link road is the description that's given here, but the game of chicken is made famous in the 1955 movie, so that's really ages ago. The 1955 movie Rebel Without a Cause starred James Dean, who later in that year tragically died in a car accident. But in this movie, the game of chicken is also played by James Dean and another guy called Buzz. They both drive a car towards the end of a cliff, and the first one who jumps out of the car is called the chicken, and the last one is, well, the hero. But you should watch this movie on YouTube, and it's really tragic. And you will see that the one that jumps up first is the chicken, but the person that jumps out last is, well, maybe the hero, but has some trouble in getting the peer esteem and enjoying it. Okay, so back to the exercise. It's a long exercise, actually. It's quite straightforward, but a lot of sub questions here. So let's get started with question A. Draw the extensive form. And this is a simultaneous move game, so you need to decide on your action before you actually know what the other person does. So the extensive form game can be drawn, but it has the decision node of team 1 and team 2. And team 2, at the point where team 2 needs to make the decision, the team doesn't know what team 1 has done. So team 2 doesn't know whether he is in this decision node or in this decision node. And this is why we have this dotted line surrounding the decision nodes of team 2, because team 2 doesn't actually know whether he is here or here. But this is the extensive form of this game. And that completes question A. Then question B, find the pure strategy Nash equilibrium or equilibria, if any. So there may be none, 1, 2, and so on. So we do it again by looking at the best responses. If you do it, then you will find the following, that for team 1, given that team 2 veers, it's optimal for team 1 not to veer, and given that team 2 doesn't veer, it's optimal for team 1 to veer. Now this is a fully symmetric game, so the same holds for the best responses by team 2, and we have two possible pure strategy Nash equilibria, one in which team 1 doesn't veer and team 2 does, and the other where team 1 does veer and team 2 doesn't veer. And these are the two pure strategy Nash equilibria of this game. Voila! And then we move on to question C. Compute a mixed strategy Nash equilibrium, and as part of the answer, draw the best response function diagram for the mixed strategies. So in this case, simple 2x2 game, so the solution is not that complicated. But let's assume that the probability is alpha that player 2 plays fear, and player 1 takes that into account. In any mixed strategy equilibrium, player 1 should be indifferent between playing fear and not fear. So that's only the case when the payoff of the expected payoff of playing fear, which is 2 times alpha, the probability that player 2 plays fear as well, plus 1 times the probability that player 2 doesn't fear, which is 1 minus alpha, is identical to the expected payoff of don't fear. And the payoff of don't fear is 3 times the probability that player 2 does fear, plus 0 times, well, we don't care because we multiplied with 0. And solving this one for alpha, we arrive at alpha should be equal to 1/2 in any mixed strategy Nash equilibrium. Now, as already observed, this game is fully symmetric, 2, 2, 0, 0 on the diagonals, 1, 3 and 3, 1 as the off diagonal elements. So also for the other team, the equilibrium probability in which the player will play fear will be 1/2. So the mixed strategy equilibrium is both players playing fear with probability 1/2. And in the diagram, this looks as follows. So if we focus on the on this dotted line, that's the best response function of player 2. Well, given that player 1 plays fear with probability 1, then it's optimal for player 2 to fear with probability 0. If player 1 fears with probability 0, then it's optimal for player 2 to fear always, so to choose 1. And as long as player 1 fears with a probability that's higher than 1/2, it will be optimal for player 2 not to fear. And then here we have the bit of the corner where the probability that team 1 fears is exactly identical to 1/2. Well, then player 2 becomes indifferent between fearing and not fearing. So he can mix between fearing and not fearing with any probability, and one of those probabilities would be the probability 1/2. This is a symmetric game, so the best response function by player 1 is exactly symmetrical to the best response function of player 2. And you can see that there are 3 points of intersection, 2 points which denote the pure strategy Nash equilibria, where one of the players fears with probability 1 and the other player does not fear with probability 1. That's the solution to question A. And on top of that, we have a mixed strategy equilibrium where the best response functions intersect as well. And this is at the point where each player chooses to fear with probability 1/2. And that's the solution that we got for question C. And this also completes question C. Then in question D, we need to assume that the game is played symmetric sequentially, where team 1 will move first and then will commit to the action by throwing away the steering wheel. Once you have thrown away the steering wheel, there's not much you can change. So, and what are then team 2's contingent strategies? And contingent means, okay, contingent on what player 1 does, what is the optimal thing for team 2 to do? And you are asked to write down the normal and extensive form for the sequential version of the game. And this is the normal form, so where we put everything in a matrix. Team 1 is the team who will move first, so he cannot make his action contingent on what team 2 does, because then team 2 at that time didn't do anything. So he can only decide whether to fear or not to fear. And team 2 has 4 possible strategies contingent on what team 1 will do, because he observed the action of team 1 before team 2 needs to make its own action. So one strategy is to fear if team 1 fears, and to fear if team 1 doesn't fear. So always fear whatever team 1 does. Or to fear when team 1 fears, and don't fear when team 1 also doesn't fear. Or do the opposite of team 1. So if we observe team 1 fearing, then team 2 decides not to fear. And if team 1 doesn't fear, then team 2 will decide to fear. And then finally, fourth strategy, contingent on what team 1 does, chooses, is not to fear if team 1 fears, and also not to fear if team 1 doesn't fear. So this is the normal form game. Looks a bit clumsy, but it is sound to write it in this way. And we can solve for the optimal actions and the best responses. And we will do that. But first we will write down the extensive form of the sequential version of the game. And the sequential or the extensive form is more intuitive, because it really depicts that, okay, we start here at decision node of team 1. Team 1 decides whether to fear or not. The dotted lines around the decision nodes of player 2 have disappeared. They were there in the previous question. Now they are not there, because now player 2 observes the action taken by team 1 at the time that he or she makes his or her own decision. So he knows at which decision node he is, and team 2 can decide, okay, I will fear or not fear, conditional on being in this node where I have observed team 1 fearing. And also, if I have observed team 1 not fearing, what is then the optimal thing for me to do? This is the more intuitive representation. Now we are ready to solve it. So I already wrote down the best responses in each action by drawing the lines under the payoffs. So if team 1 fears, then the optimal thing for team 2 is to choose the option do not fear, because that gives a payoff of 3. And if team 1 does not fear, then it's optimal for team 1 to fear. So that would mean, okay, this is if team 1 doesn't fear, it's optimal for me to fear. And that's also in this strategy. So these and these are the best responses to team 1 don't fearing. And what you can see here is that just looking from the 3 best responses, we have 3 possible equilibria. So we have always fear for team 2 and don't fear for team 1. We have as an equilibria never fear for team 2 and always fear for team 1. And we have the pair where team 1 does not fear and team 2 chooses to do the opposite of team 1. So 3 possible Nash equilibria in a normal form game, but if the game is played sequentially, then it turns out that not all of those 3 equilibria are equally reasonable. So these are the 3 that we get from the normal form version. Now we move to the sequential version of the game, and we first look at, okay, suppose that we are here, or team 2 is here, what's the optimal thing to do? Now, team 2 will then look at the payoffs of the 2 actions that he can take. If he chooses fear, then payoff will be 2. If he doesn't fear, payoff will be 3. So clearly that is optimal, and at this decision node, team 2 will decide not to fear. And also team 2 will consider what is optimal once he finds him or herself at this decision node. Well, if he fears, then the payoff will be 1. If he doesn't fear, the payoff will be 0, because then they both don't fear. They both die. Not great. So optimal thing for team 2 will be to fear. And then for teen 1, he knows or she knows what consequences his or her actions have on the decision taken by teen 2. So teen 1 knows that if teen 1 fears, then teen 2 will not fear, and the payoff to teen 1 will be equal to 1. And if teen 2 doesn't fear, then teen 2 will fear, and the payoff to teen 1 will be equal to 3. Now, deciding between these two payoffs, 1 or 3, 3 is more, so teen 1 will find it optimal to not fear. So the equilibrium outcome of the sequential game with teen 1 moving first is that teen 1 will throw away the steering wheel and not fear. Teen 1 will not change the action. Teen 2 knows it, and the best thing that teen 2 in that situation can do is to fear. So to choose X for the money, as we say in Dutch, and to beat the chicken. Okay, so that gives us one Nash equilibrium. Teen 1 will not fear and teen 2 will fear. And then in F, so some reflection on the exercise, identify the proper subgames in the extensive form for the sequential version of the game, so that's the one in question E, and use backward induction to solve for the subgame perfect equilibrium. That's what we did. And then explain why the other Nash equilibria of the sequential game, the ones that we found for the normal form, are unreasonable. Now the game has 3 subgames. So the 3 subgames are the entire game and then the subgames taking the point of the decision node of teen 2 as the point of departure. So this is one subgame, and the second subgame is this part over here. This is the third subgame. And we solve for each of these subgames sequentially. Now in the Nash equilibria of if you follow if teen 1 has feared, then it's optimal for teen 2 not to fear, and if teen 1 has feared or has not feared, then it's optimal for teen 2 to fear. So doing the opposite of player 1 is the subgame perfect equilibrium. So if player 1 fears, optimal not to fear. If player 1 doesn't fear, then it's optimal to fear. And that's consistent with, in the normal form game, this strategy. So doing the opposite as player 1 does. And the other 2 are not reasonable because the Nash equilibrium in which 2 never fears is unreasonable, because if player 2 observes teen 1 throwing away the steering wheel, then it's much better for this player to fear. And also, if player 2 always fears, it's also not the optimal thing to do, because if player 2 observes that player 1 does not fear, or does fear, then it will be optimal for player 2 not to fear. So we are left with one reasonable equilibrium, which is the Nash equilibrium, the subgame perfect Nash equilibrium of the sequential game. And that completes exercise 8.3, 4, where were we? Well, at least we're done.